Okay, I'm going to get started. Just a reminder that if you have any questions about test one or concerns about test one, you should feel free to contact me or contact your recitation instructor. And so we could talk about any questions or concerns. If there are any general questions or concerns, you can stick them in chat right now and I'll try and answer them. But if not, I'll start with today's material. And today's material is continuing last class material on magnetism. But specifically, we're going to focus on the following topic. I just saw a chat question. So if your question 16 still has not been graded, please send me an email straight after class and I'll check into why it has not been graded. I know there were a few that weren't graded by Tuesday's class, and I was hoping they'd all be graded by today's class, but if you still haven't got one graded, let me know. Okay, so we're continuing on magnetism from last class. And Lady Gaga didn't come to the test, but she has come to this test, to this class, to point out that in the last class, we met the fact that moving charges experience magnetic forces in magnetic fields. That implies that electrical currents that are moving charges also experience magnetic forces when immersed in magnetic fields. And actually the whole of today's class, entirety of today's class is really about the magnetic forces that are experienced by electrical currents immersed in magnetic fields. And we're going to look at some famous examples of electrical currents immersed in magnetic fields and their magnetic forces they experience. Oh. Okay, so specifically, I want to talk about the magnetic force on a current-carrying straight wire. So that's a very famous problem in electricity and magnetism. I want to talk about the magnetic torque on a current-carrying wire loop. That's also a very famous problem in electricity and magnetism. And then finally, this time I'm going to talk about the motion of moving charged particles in magnetic fields. So those are the three topics. So let's start with the magnetic force on a long straight wire. And an example of a magnetic force on a long straight wire might be the power cables, the power lines that, stretch across the country, stretch across the countryside. Those power lines are carrying electrical currents, and those power lines are immersed in the Earth's magnetic field. So those power lines in the Earth's magnetic field are a nice example, a nice illustration of electrical currents in straight wires in magnetic fields. They experience magnetic forces. Let's start with the case where you've got a straight wire, you've immersed it in a magnetic field, a nice uniform magnetic field. And we ask the question in that case, if the wire's carrying no current, is there any force on the wire? And so that's the situation I pictured in this slide. If you look over here on the left, This region here in the center of the sketch, that's a region of magnetic field. And with the little x's, if you remember, we're showing that the magnetic field lines are headed inwards towards the screen, inwards towards the overhead. And we've stretched a straight wire across that region of magnetic field. And there's no current flowing in that wire. There's zero current flowing in the wire. So what happens in this case? Well, look, think about the wire. The wire, although the wire itself overall is electrically neutral, the wire is actually made up of charged particles, negative electrons, positive protons. And actually those charged particles are in motion. So the electrons are in very rapid motion. The protons are in much slower motion. The electrons, therefore, individually experience magnetic forces because they are moving charged particles in a magnetic field. So any given electron in that wire, in that magnetic field, is experiencing a magnetic force. But those electrons are moving in random directions in the wire not carrying a current. And so the magnetic forces on those moving electrons, randomly moving electrons, those magnetic forces are also in random directions. So the end result is that the total force, or the net force, total magnetic force, net magnetic force on the randomly moving electrons adds up to zero. All those little forces on all the individual electrons are going to add up and cancel one another out because they're all pointing in random directions. So they all add up to zero. And there's no force, no magnetic force on a straight wire with zero current in a magnetic field. So inside it, there may be electrons and protons that are moving around. Those individual electrons and protons may experience little magnetic forces on them, but the total magnetic force on the wire, on the neutral wire, is zero. Okay. Now this slide and the next slide, these are more interesting cases. This is when a current is flowing in the wire. And in my sketches, there's going to be two cases of a current flowing in a wire. One case where the current is flowing upwards, conventional current is flowing upwards, and the other case where the current is flowing downwards, the conventional current is flowing downwards. So now let's look at this sketch. Again, I stretched a wire across this region of magnetic field, where the field lines are heading inwards towards the screen, heading inwards towards the slide. That neutral wire is, again, it's full of charged building blocks, negative electrons, positive protons. Those charged building blocks are in motion. The protons slow, let's forget about that. The electrons light fast, let's remember that. The electrons now, they have both a random motion, they're randomly moving around through the wire, but they now also have a drift motion through the wire. So that current through the wire corresponds to a gradual drift of the electrons through the wire. Now, those electrons and protons moving in that magnetic field experience individual magnetic forces. The magnetic forces that they experience due to their random motion, that all cancels out when you add up the forces and all the electrons and the protons. But the magnetic forces due to their drift motion, which is all in the same direction along the wire, the magnetic forces due to the drift motions of the electrons, those don't cancel out. They add up and make a net magnetic force. And so that net magnetic force on the current carrying wire full of moving charged particles deflects the wire. And in this sketch of the conventional current flowing upwards, so the current I, the direction of positive charge carriers would be upwards. That conventional current upwards creates a force towards the left, and that's indicated here in green. And you can see that with the right hand rule. So, take your right hand, here's my right hand, and I would point the palm of my hand in the direction of that conventional current. The positive charge carriers would move. So that's upwards, up the slide. I would curl my fingers in the direction of the magnetic field. That's into the slide. And then my thumb will point in the direction of the force. Now, if you're doing this with your hand, while you're looking at this slide, like I'm doing this with my hand, while I'm looking at this slide, I see that the force is over here towards the left. And so that current carrying wire experiences a force. Here's the other case. So this is a downward current in the straight wire. I mean a downward conventional current. The flow of positive charge carriers would be downwards. And so again, I've got a sketch of the situation. Here we are. We got this region of magnetic field again. The field lines are heading in towards the screen as indicated by the crosses. We've got a wire stretched vertically across this region of a magnetic field. And again, the question is, what is the force on the wire? Again, the answer is that that neutral wire is packed full of positive protons, negative electrons. Positive protons in slow motion, negative electrons in rapid motion. The electrons have two components to their motion. They have that fast random motion, and they have a slower drift motion. Those electrons and protons are experiencing magnetic forces. The random motion creates random magnetic forces on the electrons and protons that cancels out. However, the drift motion of the electrons, that creates a coordinated magnetic forces on the electrons, which deflect the electrons, deflect the wire. And we can again figure out the direction of the deflection with the right hand rule. So again, I'm going to take my hand and I'm going to point the palm of my hand in the direction of the current. It's downwards on the slide. And I'm going to curl my fingers in the direction of the magnetic field. So I'm doing that now. You can't really see it. It looks ridiculous. But when I do that, and if you're doing that, you'll see that your thumb of your right hand points towards the right. And so that's the direction of the magnetic force on that current carrying wire. That's the direction of the deflection of the current carrying wire. I hope that's all okay. Any questions on that? Which means it was either clear as water or clear as mud. So is the force where your thumb points, the magnetic or electric force? It's a magnetic force. So we've got a magnetic field. We're looking at a problem with this is a good question. We've got a magnetic field. That's a conveyor of magnetic forces. And so the force that arises from the magnetic field is a magnetic force. And it's a magnetic force that arises from the motion of moving charged particles. Okay, there's a second question. What is the source of a magnetic force or field? Well, in this example here, don't worry about the source. So just imagine I'm a magician that's made this nice uniform magnetic field. In the next class, so in next Tuesday's class, we're going to answer exactly that question. How do we make magnetic fields? How do we make different geometries of magnetic fields? Now, you do make them with electrical currents, or you do make them with moving charges, but I'm not explaining in this class how I made this magnetic field for this particular example. In this class, I'm explaining how a current in a magnetic field experiences a magnetic force. Oh, I want to demonstrate this. So let me share a different screen for you. Okay, so here I am. I'm not in this, but I'm beside this. Here I was in the large lecture room, chemistry, physics, and I want to show you a demonstration of the deflection of a wire that's carrying a current in a magnetic field. So in this video here, let me point out a few things. So this is called over here on the left, this is called a horseshoe magnet. I hope you can see my mouse. This is a horseshoe magnet. It's producing a magnetic field. And that magnetic field is vertically upwards from one pole to the other pole. So this downstairs here is the North Pole. This upstairs here is the South Pole. The field lines come out at the North Pole, head up to the South Pole. So this is a region of rather uniform magnetic field, like in our sketches. Then I've got an electrical circuit, basically. And that electrical circuit comprises a source of electrical current. That's this box here. It comprises a switch. It's a clever switch. I can reverse the direction of the current with this switch. And then there's a big loop of wire. And the wire basically runs through the magnet and then back around behind the magnet. And what we're going to do is, first of all, note right now, this picture was taken with no current flowing in the wire. There's no deflection here. And then I'm going to switch on the current in the wire, and you're going to observe the deflection. So look, I'm showing you the circuit. The wire goes around in a big loop through the switch, through the magnet, back around the back of the magnet. That's what I'm trying to show you there. And then back to the switch and the power supply. And there's a voltmeter and a current meter, but you can't see the needles, so it's not very helpful. Now I'm going to close the switch in one direction, and you see that deflection of the wire? So that was the magnetic force suddenly exerted on the wire when I let current flow through the wire. Now I'm going to close the switch in the other direction. You see the deflection in the opposite direction of the wire when I close the switch. And then I'm going to do this twice again. One direction, the wire is pushed away from the magnet. And then I'm going to flip the switch in the other direction. The wire is pulled towards the magnet. So it's like deflections left and right in our vertical wire in our prior slides. Okay, I'm going to go back to my slides. And I'm going to write down an equation. I'm going to write down an equation for the magnetic field, the magnetic force on a current carrying wire in a magnetic field. And I'm actually going to figure that equation out based on the equation for last class, which was the magnetic force on a moving charged particle in a magnetic field. And this is Lady Gaga's point, right? That in the last class, we explored the force on a moving charged particle in a magnetic field. In this class, we're looking at the force on an electrical current in a magnetic field. But an electrical current is nothing other than moving charges. So those two things are related to one another. And so on this slide, you know, it's a pretty busy slide, but the big picture is I'm just going to try and figure out the formula for the force on a current carrying wire from the force on a moving charge particle. So something new from something old is how I might think about it. And I'm going to try and get my pen working again here. And on this slide, let's start with the sketch at the top. Let me point out a few things about the sketch at the top. So in blue is the current carrying wire. And the green crosses are the magnetic field. They're the magnetic field lines that the wire is immersed in. And we said that that current is due to the flow of charged particles along the wire, the motion of charged particles along the wire. And here's one of the electrons that's moving down the wire. And I've tried to indicate the fact that it is both randomly moving around as it bounces between the atoms and molecules of the wire, but it's also gradually drifting from the left to the right-hand end of the wire. And so that's a picture of what's going on from sort of both a macroscopic perspective where we see the field and the current, and a microscopic perspective where we see the electrons and they're moving. So here's perhaps the key point in this equation here. The total force on the wire, that's that capital F over there on the left-hand side. That's the number of newtons being magnetic force on the wire, is going to be equal to the sum of all the little forces. That's this guy here, little fi, on all the individual electrons. So, you know, there's uppercase N electrons in this, moving along this piece of wire. They're all experiencing a little force, lowercase f with a subscript 1 for the first electron, 2 for the second electron, 3 for the third electron, so on and so forth. And so I've just got to add them all up. And that total force that emerges will end up being the number of electrons times the force that results from the drift motion of the individual electrons. So this F here is the force arising from each electron's drift motion, and this N is the number of those electrons. And so that's the basic idea, right? And if you step back from that, I mean, it looks more complicated than it is, really. You know, you got the subscripts I for the electrons, you got a sum over all the electrons, you got the big F's and the little f's. But all it's saying, right, is that the total force on the wire is the sum of all the little forces on all the little electrons. And that's just N times that average force due to their drift motion. Well, so I'm going to use this relationship between the total force on the left and this drift force over here on the right. And I'm going to fill in for N and lowercase f. So N, the uppercase N, that's the number of electrons in the wire, is the volume of the wire, so it's its area times its length, times the number of electrons per cubic meter. That's the lowercase n. So that's me just filling in for n. And then I'm going to substitute in for that little force on each individual electron due to the drift motion. Substitute in for little lowercase f. And that's from last class, that the force on each of those individual electrons due to their drift motion is just their charge times their drift motion times the magnetic field times the sine of the angle between the field and their motion, their velocity. And if I look at that equation, right, I can simplify it. I can simplify this equation and rewrite it in this form here using this equation here that we met when we talked about current earlier on in the class. It's the relationship between the electrical current in a wire and the motion of the individual electrons in the wire. So the N, the A, the Q, and the drift velocity, I can collect all those together and just write them as the current. And I get this little expression here. So I wanted you to see the derivation, how it comes about from what we learned in last class about forces on moving charged particles to get the force on an electrical current in a wire. Mostly we're going to use this equation when we talk about currents in wire and forces and currents in wire. So you've now seen where it comes from. It wasn't magic, it didn't come out of a hat with a rabbit. It is based on our understanding from last class that moving charged particles in a magnetic field experience a magnetic force. What about the direction? Well, as we mentioned earlier, the direction is nothing other than the right-hand rule. So if you want the direction of the magnetic force on a current carrying wire, again, you take your right hand, here's my right hand, and you're going to point those fingers in the direction of the current. And you're going to curl your fingers in the direction of the field. And then the thumb will point in the direction of the force on the current carrying wire. And when you do that right-hand rule to relate the direction of the current and the magnetic field and force, remember, the current is the conventional current. It's the direction that positive charge carriers would be moving. It's a direction that's opposite the direction of negative charge carriers. So it would be opposite the directions of electrons flowing down the wire. Okay, let's look at an example problem involving a long straight wire in a uniform magnetic field. And so let's look at this problem here. I wrote out the problem on the right, and I've sketched the problem over there on the left-hand side. So what does it say? It says we got a conductor that has a certain mass per unit length. So it's 0.04 kilograms per meter. So it's not telling us the number of kilograms of the conductor, but how many kilograms per meter. And it says that that conductor's hanging from a couple of wires. So at either end here, on the left, there's a conducting wire. Over here on the right, there's a conducting wire. And we got to answer the question, what is the magnitude and the direction of the current that must flow in this conductor downstairs here? So what's the magnitude of this current in the conductor that would cause that wire to kind of float in space, that conductor to float in space, i.e. the tension in the left-hand wire and the right-hand wire would vanish. So what current causes that to happen? So if you did this, if you took a conductor and you hung it from these two wires, in this uniform magnetic field, and you started varying the current in the wire, the direction of the current in the wire, the size of the current in the wire, you get different magnetic forces, different direction magnetic forces, different size magnetic forces. There's a particular current size, current direction, that actually is equal and opposite gravity's pull on that conductor. And when that current produces a magnetic forces equal and opposite to gravity's pull, that wire is going to float. And that's the situation that we're thinking about. The wire is kind of floating there. There's no tension needed in the left-right cables, left-right wires. So that's the situation. Okay, so with that understanding, I first set about answering the question of what's the direction of the current. So let's look at this sketch here. Oh, down here. So the key thing is that I know that gravity, the force of gravity, is pulling this conductor downwards towards the Earth. And if the conductor is floating in space, then there must be a corresponding force, a balancing force that's pulling the conductor upwards. And that's coming from the magnetic force that's coming from the magnetic field. So this is this situation where the wire or the conductor is floating in space, where the downwards pull of gravity and the upwards force of magnetism are equal and opposite one another. So the blue arrow of gravity and the green arrow of magnetism are equal and opposite here. So what direction must the current be to get an upwards magnetic force? Well, you could just try this out, right? The current could either flow left or right along the wire, or it could flow right to left along the conductor. So you just try out those two cases. So again, I would use my right-hand rule. So I try this out with this figure. I'm going to point my right hand in the direction of the current, which, say, I've sketched it here towards the right. And if I do that and curl my fingers in towards the screen, I'm doing that right now, I find that my thumb points upwards. And so that direction of current does indeed produce a magnetic force that could balance gravity. If you point the palm of your hand in the direction, the opposite direction, from right to left, so I'm doing that now, and then I curl my fingers in towards the screen, now I would get a force that is downwards. So that would not balance. That could not counteract gravity. So it must be the current's flowing towards the right. The current can't be flowing towards the left. So that's the direction. So what about the size? Well, here I'm going to calculate the size. So I reproduced the picture on the left, but now I'm calculating the size of the force. And all this slide, just to be clear, when I write down F's, forces, I write down an Fg, force of gravity, I write down an Fb, force of magnetism. I'm thinking about the sizes here. I've answered the question about the direction of the current. I've thought about the directions of the magnetic field, the magnetic force, the gravitational force. I'm just worrying about sizes now. So that's the context of this statement up here, my starting point, that the size of the gravitational force downwards must be equal and opposite to the magnetic force upwards. So there's a question in chat, is FB always FG? Are these always equal and opposite? No. So if you were to change the current in the wire, they would not be equal to one another. This is the special case where the wire is floating in the gravitational magnetic fields. And there's one special current that causes that floating of the wire in the gravitational magnetic fields. And that current is what we're trying to figure out. So there's only one current that will do this. One, it's like the magic current that floats the wire. Okay, so the condition for the floating wire is the gravitational force is the same size as the magnetic force. I can fill in for the gravitational force, just mg. We remember that from last semester. And I can now fill in the force, the magnetic force, due to the current flowing in the wire. So that magnetic force we figured out was the current in the wire. So more current, more force, times the length of the wire. So the length of this section of wire here, that's the L, times the magnetic field that it's immersed in. So more magnetic field would make more force, that makes sense, times the sine of the angle between the direction of the current and the direction of the field. Field is perpendicular to the slide, the overhead. The current is in the plane of the slide or the overhead. So there are right angles. So that's sine of 90 degrees, and sine of 90 degrees, you know, is 1. Well, look, we've made an equation for based on this sort of balance between gravity and electricity that contains the current that we're trying to figure out. So at this point, we just need to rearrange it for the current. So I divided by L and B. That's all I had to do. And I noticed when I did that, that the current is equal to m over L, mass per unit length of the wire, times the ratio of the acceleration of gravity divided by the magnetic field. And it's useful to think of it this way because m over L was what we were told about the wire. We weren't told the mass of the conductor. I don't know how many kilograms it is, but I'm told that it's 0.04 kilograms per unit length. And that's all we need. We just need the mass per unit length. We don't need the actual mass of the conductor. So I can fill that in. That's this number here. And then, you know, we're immersed in a gravitational field. Here's the gravitational field, or G. We're immersed in a magnetic field. Here's the magnetic field. That's 3.6 Tesla. And that's the reason that there are two forces. That's the reason there is this balance between the forces. And when I multiply all these numbers out, this is the current you need. It's 0.11 amps or 110 milliamps. That's the magic current that floats the boat, that floats the conductor in the magnetic gravitational fields. Any questions on that before I go on to next topic? Okay. So next topic is example of forces and torques on a loop of wire. So that was a straight wire. Now I'm going to talk about a loop of wire. And like we got a interesting equation formula for a straight wire in a magnetic field, we're going to get an interesting conclusion equation for a current loop in a magnetic field. And this, we're going to return to loops of wires and magnetic fields later on, because actually understanding loops of wire in magnetic fields is the heart of understanding the electrical motor, it's the heart of understanding the electrical generator. It's the heart really of our modern lifestyles, technological lifestyles. We make the current that comes out of the outlets by, you know, loops of wire that are moving through magnetic fields. That's how we generate electricity. We use electricity often to make motion by loops of wire in magnetic fields. So our modern lifestyles, our understanding of our modern lifestyles is based on loops of wire carrying currents in magnetic fields. Okay, so here's a picture of the situation here. And first I'm going to discuss the forces on a loop of wire in a magnetic field, and then I'm going to talk about the torques on a loop of wire in a magnetic field. So this one we're doing both forces on the loop and the torques on the loop. This slide is the forces. So in my sketch on the left, I've got a rectangular loop of wire. Here we are. And a current is flowing around that loop of wire. So it's going right to left in the top arm, then it would be going downwards in the left arm. It would going left to right in the bottom arm. Yeah, here it is. And then it's going upwards in the right arm. So that's the current, and it was even told the size, the size of the loop. So the dimensions of the loop, if we look here, are its width is A and its height is B, and it's a rectangle. So that's all the information about the loop. And then there's a magnetic field. You see a sketch of the field vectors here. So this field is sweeping from left, to be clear. It's really sweeping from left to right across the region of the loop. So those would be some field lines. And so now we've got a current loop in a uniform magnetic field, but actually, let's remember the problem we just solved of straight current carrying wires in a magnetic field, because this current loop in a magnetic field is nothing really other than 4 straight current carrying wires in a magnetic field. 2 of the wires are horizontal in my sketch, 2 of the wires are vertical in my sketch, but they are just straight current carrying wires. And so based on that, I've cleared up the picture so we can see it. I've written down 4 statements about the forces on the 4 sections, the 4 straight sections of the wire. So there's a left and a right, and I've called those forces F1 and F2. F1 is the force on the left, F2 is the force on the right, straight section of the loop. And then there's a top and a bottom, upstairs here, downstairs here. And I've called F up and F bottom the forces on the top and the bottom. So let's just go through them and figure out the forces from this magnetic field that the wire is immersed in. And let's remember the master equation that we developed in the last topic, that magnetic force on a current in a magnetic field is given by this equation. F is the force, B is the field, I is the current, and then there's the length of the wire and the orientation of the wire, are the L and the theta. Okay, so there's a question in the chat, I just spotted it. Question is the field in the plane of the loop? Yeah, so the field lines are sweeping across the overhead just from left to right. They're not coming out of the overhead or going into the overhead. The loop is also in the plane of the overhead. And so this is kind of like viewing this situation from the side, viewing the loop of wire, the rectangular wire from the side. I hope that's clear. Okay, so let's answer one by one these 4 forces on these 4 sides. So let's start with F1. That's over here on the left. So the F1, the current is down, the magnetic field is towards the right. And so to figure the force, you've got to point the palm of your hand down. you've got to curl your fingers towards the right, and then your thumb will naturally point in the direction of the force. So when I do that, I see the force is perpendicular to the field lines and perpendicular to the current. It's out of the overhead, out of your screen. So that's the force there. If I do the same thing over here on the right-hand side, right, again, I would point the palm of my hand in the direction of the current. I would curl my fingers in the direction of the magnetic field. Again, remember, you're seeing this in a camera, so my left pointing fingers become my right pointing fingers and vice versa. You've got to do this yourself. But if I do this, I find that the force here, because the current is reversed, the force has reversed too. Now it's into the screen. And I could write down the sizes of those forces with my equation. That's what I did here. It's the current times the length of the wire times the magnetic field times the sine of the angle between the field and the current. That's 90 degrees in this geometry. So it's sine of 90 degrees. The sine of 90 degrees is 1. And so we just get simple equations for the forces on the left and right sides in this case. The magnitudes of the forces are just I little b times uppercase B. So the lowercase b is just the height of the loop. The uppercase B is the magnetic field. So you could do the same thing for the top and the bottom. Here's the current in the top. Here's the current in the bottom. But remember, right, we said that if moving charged particles move in the direction of the field or opposite the direction of the field, the magnetic force is 0. Also means that if the current is in the direction opposite the direction of magnetic field, the magnetic force will again be 0. So there is no force on the top and bottom. There's no force because the direction of the current or the direction of the motion of the charged particles is either parallel, anti-parallel to the magnetic field. And so that's what I've written here. Top and bottom have no forces on them, and the left and right have forces into and out of the screen that are actually equal in size. So there's a second follow-up question. So the magnetic force is always perpendicular to the magnetic field and the current. Yeah, that's a really good point to make. We did make it last class. I don't think I made it again this class. But the key thing is that magnetic forces are always at right angles to the fields. They're always at right angles to the direction of the current or the direction of the motion. So it's a very peculiar thing about magnetic forces, quite unlike electric forces. Remember, electric forces are always in the direction or opposite the direction of the field. It's much simpler for electrical forces, much more complicated for magnetic forces. Okay, so this is our end result of considering the forces. Now I want to come up with an equation for the torque on the loop. And to help us understand the torque on the loop, I want to, I want you to look at this sketch on the right. So now I'm looking, in the previous slide, I was kind of looking from the side at the loop. Now I'm looking, say from the top down on the loop, or it could be from the bottom up on the loop, either of those two cases. So I'm taking a different view of the loop, and I'm going to see a different view of the loop, and I'm going to see a different view of the forces. There's a question in the chat. Wouldn't F1 and F2 both be directed towards the left? No, they're directed either out or into the screen. They've got to be at right angles to the magnetic field, and they've got to be at right angles to the currents. And they're going to be in opposite directions because the currents are in opposite directions. So the directions of the forces on the last overhead were correct. Okay, so here's the loop. We're looking from the bottom here, I'm saying. It could also be looking from the top, I guess. And here we see the forces. And the key point here, remember the forces were perpendicular to the face of the loop and they were in opposite directions. So in this sketch, one of them's up and one of them's down. F1 is up and F2 is down. So look, what would this arrangement create? Well, this is the kind of arrangement of forces that you use to open a door, about a hinge. These forces will create rotational motion, like your force of your hand opening a door creates rotational motion. If you think about it, let's imagine the motion of the loop about its center, about its axis here. The force F1 on the left, which is upwards, will tend to turn the loop clockwise. The force F2 on the right, which is downwards, will again tend to turn the loop clockwise. So these two forces work in concert, work together to rotate the loop. And that's what we call a torque. Forces acting at these locations create a torque. Torque is the generator, the source of rotational motion, like forces are the generators of changes in translational motion. And so this is an important picture. It leads us to an equation for the torque on the loop due to the magnetic field that the loop is immersed in. So first thing is that the total torque, that's the tau here, is going to be the sum of the torque due to the force F1 and the torque due to the force F2. They're going to add together. Now, here I'm remembering that forces and torques, they're vector quantities. And so you've got to add together the vectors. You've got to take account of their directions. In this case, things are simple because both forces create torques in the same direction, the clockwise direction. So from this point onwards, I'm just going to think about the magnitude, total magnitude of the torque on the loop as being the sum of the magnitudes of the arising from the torques from force number 1 and force number 2. So that's what I'm doing in this second line here. And I'm filling in the definition of torque in terms of force. If you remember, the torque due to a force is the size of the force times the distance the force is applied from the axis of rotation times the sine of the angle between the direction of the force and the line drawn from the axis of rotation to the point where the force is exerted. So if you think of that for force number 1, here's its strength, represented by this arrow. It's at a distance of a/2, half the width of the loop, from the axis of rotation. So this is a/2. And its direction is 90 degrees with respect to the line that runs from the axis of rotation to where the force is exerted. So that's 90 degrees. And so that's the torque created by force number 1 and the torque created by force number 2, same equation, because it's the same, it's actually the same strength force at the same distance from the axis of rotation with the same orientation with respect to that line from the axis of rotation to where that force is exerted. So everything's the same. So then I just substituted in for F1 and F2, the two forces. They're both the current times the field times the length of those wires, those sections of the loop that are experiencing these forces. And then I just collected together these two terms. I collected together all the common factors in these terms. It's this equation here. And I noticed that A times B, little a times little b, that's a friend of ours. That's the area of the loop. That's this equation here. And so finally, we end up with another fantastic master equation, right? The torque that's exerted on this loop in a magnetic field, that torque is equal to the field strength times the current times the area of the loop. It's a very simple equation that we've figured out by understanding the forces on the loop based on the previous section we just discussed. So that's an important equation. There is a sort of generalized version of that equation. So this slide, oh crap. This slide is the talk on, I've done it again. It's going to take me years of therapy to get over doing this every class. It's becoming a nuisance. This is the talk on a general current carrying loop. So the prior slide, if we just go back to the prior slide, if I can do that, that was the talk on a rectangular current carrying loop. And we figured that equation out. Now I'm going to show you the equation for a general current carrying loop. What do I mean by general current carrying loop? What I mean is, what's the difference between the rectangular current carrying loop and the general current carrying loop? Let me explain that. The general current carrying loop, when compared to that rectangular current carrying loop, can have not just one turn of wire, one loop of wire, but it could have many loops of wire. And the number of loops of wire, I'm just going to call N, uppercase N. And that uppercase N is here. Also, this general current carrying loop, it can have any shape. It doesn't have to be a rectangle. It could be a circle enclosing some area, or an ellipse enclosing some area, or something more complicated. The A here is the enclosed area inside the current carrying loop. And that may be a circular, a rectangular, a square, or some other shaped area. And then finally, the theta here, to make it perfectly general. In the last example, the area vector that would represent the current carrying loop, it's at right angles to the surface that's enclosed by the current carrying loop, was at 90 degrees to the magnetic field. In this case, in this general case, here's the area vector that represents the area of the current carrying loop. Here's the magnetic field vector that represents the magnetic field that's immersed in. And the angle between them is now theta. So this is a more general equation. And so that's the theta here. So you see the equation for the torque on a rectangular current carrying loop that we met on the last slide. You see the I times the A times the B. The sine of theta would be 1, but we've expanded that equation so that the current carrying loop can have lots of turns, it can have any shape, and it can have any orientation. And so this is a very, very general formula for the torque on a current carrying loop in a magnetic field. I'll make one point about it, that this piece here, NIA, so that's all about the properties of the loop. It's nothing about the properties of the magnetic field. It's the number of turns of the loop, it's the current that's flowing in the loop, it's the area of the loop. We call that NIA, that embodies all the characteristics of the loop. We call it the magnetic moment of the current loop. So NIA, we call the magnetic moment. We often give it the symbol mu. So I mentioned that. Okay, let me demonstrate that. So we've just come to the conclusion, right, that in a magnetic field, if you put a current loop in a magnetic field, you're going to get a torque on the loop that's going to rotate the loop. And so let's see if we can demonstrate that. So I'm going to share a different slide. And so I hope you can see this. I'm back in chemistry physics. And what I've got in this overhead is I've got a, here's the horseshoe magnet again. This was the magnet from the last demonstration. It produces a magnetic field that goes from one of its poles, this is the North Pole on the right here, to the other pole. This is the South Pole here. So there's magnetic field lines that are sweeping from left to right. I've got a loop of wire. It's actually many turns of wire. So it's like a general loop of wire immersed in that magnetic field. And that loop is here. And that loop of wire is actually connected. It's made into an electrical circuit. You can see a lead coming in on the left, a lead going out on the right. So there's a power supply over here on the right-hand side. Leads come out of the power supply. They go through this switch, which is a clever switch where you can reverse the current, and it will push a current or deliver a current to this current loop. And so let's watch this video if I can. So I'm going to show you the circuit. So here, this is out of the power supply, through the switch, up the stand. Where's my hand gone? And then back down the left-hand side and around the loop and back up the right-hand side, back down the stand, over to the reversing switch and back to the power supply. And the power supply will show us the voltage and the current that's drawn, but we can't actually see it. And there's the horseshoe magnet with the magnetic field. Right now, there's no current. The switch is not closed. As soon as I close the switch, look, there is a torque. There's this torque on this current loop that rotated it. When I open the switch, it goes back to its original position. It just floats there. Then I'm going to close the switch again, but the opposite direction this time. I get a torque in the opposite direction. Fantastic. Then I open the switch and it goes back to its original position, no torque. And I think I'll do that one more time for each direction. Rotates one way, go the other way, and it'll rotate the opposite direction. And so that equation that we figured out, equation that we worked out from our understanding of magnetism, we've just shown that a loop of wire, or loops of wire do indeed experience torques in magnetic fields. So that's a big step. That was a sophisticated problem we just solved, I think. Okay, I got a quiz question. So let me get this going. Okay, let me answer this question, this quiz question. So if you remember, the vertical sides experience forces, the left and right experience forces, the horizontal sides experience no forces. But also, if you remember, the vertical sides experience forces of the same size when we calculated it, but in opposite directions. So if you actually add up all the forces that are acting on the rectangular loop, two of them are zero to start with, and the other two are equal and opposite, so that there's no net force, no overall force, no total force on the current carrying loop. Okay. in the last 5 minutes, I just want to talk a little bit about magnetic forces on moving charged particles and the motion that moving charged particles undergo. And one of the very interesting things about the motion of moving charged particles in a magnetic field, in a uniform magnetic field, they undergo circular motion. And so I want to show you, it's a very beautiful motion that happens when you put a moving charged particle in a magnetic field. And I just want to show you how that works, how the circular motion works. There's a couple of examples in these slides about the circular motion. I know I won't get to the examples about the circular motion, so maybe I'll put a extra video where I solve one of them separately into our Canvas course. Okay, so this is a sketch of the situation I'm thinking of. I'll go get my pen going again. So if you look over here on the left, I've got a moving charged particle. So I've pictured it at several different times in its motion. So over here on the left-hand side, here's this positive moving charged particle. This moment it's moving kind of down and towards the left. And then later on, I've captured it here. Here it's moving right. And then later on still, I've captured it here. This moving charged particle is now moving upwards. And actually, it's executing a circular motion. It's executing an orbital motion. And so we're going to see how that emerges. It emerges because it's in a uniform magnetic field. So there's a B field here. And that B field, from the little crosses you can see, is pointing into the overhead. And that will cause, if I launch this particle in this uniform magnetic field, it will cause this circular motion. And so let's see how that happens. And you can see how this happens with the right-hand rule. So if you start over here on the top left, the motion is towards the left and downwards. So you would point your palm of your hand left and downwards. You would curl your fingers into the screen. That's the direction of the magnetic field. You find that there's a force in this direction. It's at right angles to the field and the motion. If you did the same thing at the bottom, you pointed the palm of your hand in the direction of the motion, the velocity vector v, and you curled your fingers into the screen, you'd find the force was upwards. And if you did the same thing over here on the far right, when the motion is up and you curl your fingers into the screen, you find that the force on the positive charge particle is over here towards the left. Look, all these forces are acting towards a common point. It's actually the center of the circular motion that this particle is undergoing. So this particle is undergoing circular motion because of this centripetal force that's due to this magnetic force. So magnetic forces in this situation will cause a centripetal force, and we'll get this beautiful circular motion. Now we can turn that into an equation that tells us, the speed of the circular motion for a given radius of the circular motion. And that's what I've done over here on the right. I've spotted now that the magnetic field creates a magnetic force that causes a centripetal force that leads to circular motion. I've spotted that from my picture and my right-hand rule. Now I'm going to figure out the mathematics of that, how the speed and the radius of the circular motion are related to one another. So the starting point is that the centripetal force that we need for the circular motion is provided by the magnetic force. And that it must be that the size of the centripetal force and the size of the magnetic force are equal. So I plugged in the equation, if you remember from 211, this is the equation for the centripetal force. And I plugged in the equation for the magnetic force. This is QVB sine theta, but there's 90 degrees between the motion and the field, so the sine theta is 1. So I get this equation here. And if you rearrange it, you get this relationship between the velocity as it goes around the circular motion and the radius of the circular motion. And that relationship between the velocity and the radius depends on the field. So the bigger the field, then for a given velocity, the radius would be smaller, or for a given radius, the velocity would be bigger. And it depends on the characteristics of the particle. It depends on the charge and the mass of the particle. That's the Q over M. And so that is a slide that tells you that in a magnetic field, a moving charge particle, uniform magnetic field, a moving charge particle will execute this kind of beautiful circular motion. Actually, it's even better than that. Let me just show you the picture from the next slide. That was kind of a two-dimensional picture. It's like we're living in a two-dimensional world. We've got a plane, we've got a magnetic field perpendicular to that plane, just watching the circular motion. But in three-dimensional world, if you put a moving charge particle into a magnetic field, if you launch it into a magnetic field, you get these beautiful helixes, where if you focus on the rotational motion of the helix, it's just that circular motion from the last slide. That's the motion perpendicular to the field. And then that's superimposed on a motion that's parallel to the field, where the particle just glides along the field lines. And so you get this beautiful helical motion of moving charge particles in magnetic fields. Here's a picture of it, and this is where I'm going to end. This is where I truly did. If we were in the large lecture room, we could have demonstrated this, but I couldn't get the video of this to work. I'm launching charged particles into a region of magnetic field. It's perpendicular to the page. They experience a magnetic force in the magnetic field that provides a centripetal force that creates this circular motion. And we're seeing the circular motion because the particles, the moving charge particles, they're electrons, moving charge electrons are moving through a gas and they're causing the gas to glow. And so this is a demonstration of the circular motion of moving charge particles in a magnetic field. I'm going to end there. Again, I've overrun, stealing time from you. Three things we did today. Let me just remind you that we talked about magnetic forces on a long straight wire, big famous problem in physics. Talked about magnetic torques on a current loop, another big famous problem in physics. And then finally, we talked about the motion of charged particles in magnetic fields, where they execute circles or helices. Again, it's a famous problem, big famous problem in physics.